I want to do an example with Newton's second law about holding the book against the wall. I really like this problem because it's absolutely impossible to do without a very good visualization of what's going on. So I have some book held against a vertical wall with some pushing force I'll call P. And that pushing force is made with some angle theta relative to the vertical. And I want to know what range of pushing force, what range in the magnitude of the pushing force keeps the book from falling. What range of P holds the book up? And all of a sudden, that's a little weird. So what a range? Have we had a question that asked exactly that before? What does that mean? What range of P holds the book up? So let's think about it. How are we going to hold the book up? There's some coefficient of static friction mu between the wall and the book. And so I can say, well, if my pushing force gets really, really weak, in fact, in the limit that I let go, the book is going to fall. However, if I start pushing really, really hard, as the pushing force gets very large, it's quite reasonable that then I would push the book up the wall. There's some sort of range above a minimum and below a maximum that holds the book in place. So I need to find what that range is. The other thing I want to ask is what relationship between theta and mu, or is there one? Oh, that what we say there's a relationship between theta and mu that must be true, or no force P will make the book slide up. So presumably there's some range P that holds the book up, but that under certain conditions there is no maximum value. So I want to find that as well. Okay, so I'm going to tackle this with Newton's law again. So the first thing I have to do is choose an object. I really only have one object, so I'm going to choose the book. And so what are the forces on this book? I have gravity. That's always a good one. Now I have this contact force from the push. So as a contact force, do I need to split it up into normal and frictional components? Probably not. I'm interested in the magnitude of this pushing force. I'm given it relative to an angle relative to a vertical. So I'm just going to leave it as a contact force. I'm going to assign it a vector, call it the p vector. And I'm going to take this moment to talk a little bit about that. So some students will see P here and think this is some new type of force. It's a pushing force. But it's not. It's a contact force, just like all the contact forces we've had so far, and we have a model of a contact force. I'm calling it P vector because that's a letter that when I see that letter, I think in my mind that is the contact force of the person pushing on the book. I don't see P, I see contact force. And that's an important distinction and something to think about. When you write these letters on the page, you should be what you have on your page are things like G, F, theta, mu, P. And a lot of students who are solving problems for the first time, in their head, what they read is, and the words they have in their head are P, mu, theta, G, F. But that's not what you want. though these are just shorthand messages, shorthand notes that represent real physical quantities. And in your head, you have to have the real physical quantities so that when you see P, you read the contact force pushing against the book. When you see mu, you read the coefficient of friction between the book and the wall. When you read theta, when you see theta, what you have in your head is the angle of the pushing force relative to the vertical. See, eventually your page just gets cluttered with all these Greek and Roman letters. And if you just read them as Greek and Roman letters, it all becomes gibberish, and you'll never get the right answer. You'll be so prone to mistakes. And the way to keep that clear is that in your head, you always read what those parameters represent, not the letters themselves. Okay, well, let's continue. The other force here is the contact force between the wall and the book. So I know that friction is helping to hold it up. So I'm going to break that contact force into the normal force, which I'll call N, and the friction I'll call F sub F. Okay, fine. So let's get a free body diagram going here. Those are my forces. So I have a dot in the center. My forces, I'll have my tail at the dot. So that's the force due to gravity. I'm going to have some coordinate system here. So let's set up sort of a XY axis. Sometimes I put my x-axis on. Sometimes I just keep it off my free body diagram if I think it clutters too much. But so let's make my green here. So there's my force due to gravity. I have this contact force that has some angle relative to the wrong theta. My angle is relative to my vertical. So that's here, right? If I sort of extend, well, wrong color. I extend my force relative to the vertical axis, then if this is theta, then that's theta, which translates to this angle theta. So that you have to be careful that we translate our picture to our free body diagram carefully. Okay, so now we have a normal force. That's perpendicular to the surface, pointing from the agent to the object, the wall to the book. Okay, finally the frictional force. So where does that point? Well, that's a conundrum. Because, so from our static frictional force model, the frictional force is going to point in the opposite direction the object would move relative to the agent if there were no static force present. Well, what direction would it move? Well, that depends. It depends on the strength of the pushing force. If the pushing force were really small, not enough to hold up the book, and there were no frictional force, it would fall. But if the pushing force were really strong, and there were no frictional force, then the book would slide right up. So we have to look at two separate conditions. We have to do two separate conditions here. Have to, may be strong, but I think we want to, because we really have the frictional force is going to point in different directions depending on the strength of the other forces. In fact, to convince ourselves that that's true, let's just take a look at what we have right now. I mean, if in the y direct, we know that the frictional force is going to point in the y direction. So if we look at this contact force, this pushing force, it's going to have a y component that's up, that points in the positive y direction, and then a positive x component. And so I can see that if the pushing force were really small, it's going to be less than the force due to gravity. If it's large, it's going to be greater than the force due to gravity. And at the point where the component of this pushing force is the same magnitude, but in the opposite direction, as this force due to gravity, at that point, the coefficient of static friction goes to 0. There is no frictional force at that moment, because the component of the pushing force, the vertical component of the pushing force, exactly matches the force due to gravity. If the magnitude is any less, then the book wants to fall, and the frictional force helps keep it up. If the pushing force is any larger, then the frictional force is down to help prevent the book from sliding up. So that's where, so given that there's this condition where, depending on the magnitude of the pushing force, the frictional force changes sign. Let's look at these two regions separately. So first, we'll look at small values of this contact force P. So in this regime, then, the frictional force points up because it's helping support the book from falling, because the contact force holding it up is small. All right. So given that we got through that, and so this is a great example where there's no formulas for this. There's no equations that tell you this. You have to be able to understand the problem and be able to extract logically information from the problem necessary to solve it. All right, so now we have our forces. Let's go ahead and do a vector sum of all of our forces. So we have a this contact force has some component in the x direction plus some component in the y direction. And so that's, again, I'm looking at the length of that triangle side and the length of that triangle side. And then from my coordinate system, I note that both components are positive. And so my force due to gravity has nothing in the x, but the entire magnitude is along the y. It is a magnitude mg, and from my diagram, that's negative. And then I have the normal force, which has some magnitude in the x direction that from my diagram is negative, and it has nothing in the y. And then my force due to friction, which is nothing in the x, and under this condition has some magnitude mu sub n in the y that is positive in this regime where p is small. And by p is small, I mean the vertical component of p is less than mg. So really, I can identify that here. P cos theta less than mg is the region that I'm looking at. Okay, so these are my forces. I'm going to sum them. These are equal to my mass times my acceleration, which my condition is that I'm holding the book against the wall. It's not moving. So my acceleration in both directions is 0. So that gives me my two relationships in 2 dimensions between all my important components. I have that P sine theta minus n is equal to 0, and P cos theta minus mg plus mu sub n is equal to 0. All right, I want to know the condition on P. I know theta, mg, and mu. I don't know n. Again, and I know them in the sense that the problem says I've been given those, but I don't have a number for them. I'm solving everything in terms of arbitrary values. Okay, so n, the first equation gives us n is equal to p sine theta, so that I can substitute into there, and that gives me p cos theta minus mg plus mu p sine theta is equal to 0. And so now I can solve this for p. I can pull out a p from each of those terms. P then cosine theta plus mu sine theta is equal to mg, or p is equal to mg over cos theta plus mu sine theta. Okay, so what does this mean really? And so this is one regime. So where this is small, this is the small value of p. So this gives us a limiting case really, as if p is any smaller than this value, then the system fails. Then mu can take it can't hold up the system, right? So mu it takes on some maximum value as p shrinks, right? Mu changes so that the system remains static. But if but mu can only take on some maximum value, at which if this drops any further below, then the system falls. So the p has to be larger than this expression. Okay, so now let's look at the other condition where we have for large p. So in this case, missed my spot there. Okay, so we have p at some angle theta. We have F sub g, the normal force, and in this case, the frictional force is down because it's now helping support the block from the book from being pushed up. Okay, so it turns out that I have exactly the same system I had before, only in this case, this changes sign. But we can do that pretty quickly. So we have, what do we do? Push force first. So our push force is equal to p sine theta I hat plus p cos theta j hat, and then gravity. Force due to gravity, 0 I minus mgj. Then normal is negative n I, because we have plus x plus y plus 0 j. And our force due to friction, this is what changes, 0 I and negative mu n j. This vector sum, mass times acceleration, which, if it's not moving, is this. So our two relationships, again, from here, and I have p sine theta equal to n, that's from this expression, and then I have p cos theta minus mg minus mu sub n equal to 0. And this is now, again, a limiting case. Mu is the coefficient of static friction. It takes on whatever value up to a maximum that can stop it from going up, and then any further the p will push the book up the wall. All right. So if we substitute in then for n in here, we get p cos theta minus mg minus mu p sine theta is equal to 0, or p cos theta minus mu sine theta is equal to mg, or P must be less than or equal to mg cosine minus mu sine theta. So this is, if you want, when I go from my equal sign to my less than or equal sign, what I'm really doing is replacing the coefficient of static friction with its maximum value. So this is going to be true here. They're equal, but the coefficient here just changes its value so that the equality is valid. But eventually it comes up to some maximum value, and that sets the limit at which the system is no longer at rest. And it accelerates. And so the pushing force has to be less than this value. And so since this is in the denominator, this increases as this becomes smaller and this becomes larger. But as this reaches some maximum value, then this denominator of this fraction can't become any smaller, and so any larger amount of pushing force slides the book up. So we now have the answer to our problem, which is mg cos theta plus mu sine theta must be less than or equal to our pushing force, which must be less than or equal to mg cos theta minus mu sine theta. Yeah, I see that I missed my theta there, but so this is the answer to the first part of the question, the range over which the system stays at rest. And it took a lot of understanding what's really happening in the problem itself. And so from this, can we answer the second part of the question? Is there a relationship between mu and theta such that no force P will make the book slide up? And there is. That's this second condition here. P must be less than this. Well, let's look at the denominator here. Depending on what mu is and the angle, this can become arbitrarily small. So as cosine theta minus mu sine theta goes to 0, then this limit here goes to infinity. So this sets the relationship. So if I say, so in fact, cosine theta must be greater than mu sine theta, or else this goes to infinity, and P can be anything it wants. So this sets our relationship. It says mu must be less than cotangent of theta. So the coefficient of friction must be less than cotangent of theta, or else no amount of pushing force will slide the book up. And so what does that mean physically? What that means is the friction is large enough and the angle is large enough so that as you push harder, you're contributing more to the frictional force holding the book to the wall than you are supplying a vertical component of the pushing force trying to accelerate it upwards. So that's what the physical meaning of this condition means. All right. So what did we learn? We followed a lot of the same procedure, but we can't get away from our original strategy, which involves visualization and brainstorming. You have to have a very good picture of what's physically happening in the problem, and often you need to be able to extract information from the situation to be able to solve the problem.